All right, so let's get started. Um, so the reminders items here, homework 6 due on Tuesday. All right, and then exam 2 will be about roughly little bit more than 1 week from now. Um, Classroom in seat for disinfection today, Tareen and Aliyah. Okay. All right. So last time we got started with chapter 6 on uniform circular motion. All right. So let's have a quick review on what we mentioned last time. So for circular motion, then you have circular or angular position. We define that. So it's the angle measured from a reference line. Okay, just like position is measured from a reference point at the origin. So this is similar here, but you have a reference line over here, and the angle is in radians for the SI unit. And radian is also treated as dimensionless. Okay, so sometimes you see people just write down 2 pi as the angle without mentioning the unit of radians, so that's fine. By convention, you take counterclockwise direction as the positive direction of this position. Okay, and then clockwise to be the negative direction. All right. And we also took a look at the angular velocity. So then if you are doing average velocity, you do change in position over change in t. In this time, change in angular position over change in t. Okay. So then SI unit for the angular velocity should be radians per second or just per second. Okay. All right, and then relationship between linear and angular displacement. So angular displacement is equal to linear displacement divided by r. Okay, so that's the arc length for the linear displacement. Okay. Also, I think we look at the relationship between linear and angular speed, just the magnitude wise. Okay, so then angular speed omega is equal to linear speed divided by r. Okay, similar to the displacement relationship between the displacements. Okay, we also took a look at the acceleration. So if you have uniform circular motion, then the acceleration is always pointing towards the center of the circle, so that it's called centripetal acceleration. Okay, and the acceleration can be either equal to v squared over r, the linear speed over r, or the r times the angular speed. Okay, square. All right. Then we apply Newton's second law to the uniform circular motion. So then force in this case would be having the same direction as the acceleration. So it's also called centripetal force equal to mass times the acceleration. Okay, centripetal acceleration. So because centripetal acceleration has two expressions, then net force or centripetal force also you can have two expressions. Either it's mv squared over r or m times r times omega squared. Okay. I think that's what we learned last time. We also look at a couple examples. So today we are going to start with this example here. So this says as a circus act, a person drives a motorcycle with constant speed v around the inside of a vertical track of radius r as indicated in the figure. If the combined mass and of the motorcycle and the rider is m, find the normal force exerted on the motorcycle by the track at these 3 different points, A, B, C. And then D, if the track has a radius of r equals to 10, what minimum speed he needs to maintain to get over point C without falling off the track. Okay, so I'll give you guys a couple minutes to see if you can come up with a plan on this one, and then we can take a look on this one together just in a couple minutes. Okay. All right, so let's take a look here together. It says, so from the figure, it shows that um, so that it says combined mass of m and then speed of v, as the figure shows at point A, B, C, they are the same. The radius is r. Okay. So if you look at the free body diagram over here, so there's a mass here, there's a normal force there. Okay. So let's see. And because the speed is constant here and there it's constant, so we can assume that speed is constant throughout. Okay, so then in the tangential direction, we are not expecting any net force because the speed in the tangential direction, that's constant. Okay, now we can just focus on the direction that is perpendicular to the tangential direction here. So that means towards the center here in this case. All right. So for normal force and then weight, so the net force in this case should be equal to um, normal force minus the weight. Okay. Now because the rider and the motorcycle um, it's in the circular motion here, so then we can expect that there's a centripetal force or net force equal to the centripetal force, which is mv squared over r. Okay. So that's in this direction. All right. So combine these two, you can write that m minus mg is equal to mv squared over r, right? And then you're looking for normal force, the track exert on the motorcycle. So the normal force should be equal to mg plus mv squared over r. Okay, so this is part A here. Now we are not given any numbers, so you can just express this in an equation like that. Okay, so express n in terms of the other quantities given. All right, so this is A at point A. At point B, it's over here. All right, so I'm not going to draw the full picture, but at point B here, you can make now imagine there should be a weight as usual, right? mg, and then there's normal force there. Okay. All right. So then again, we can just focus on the direction that is pointing towards the center of the circle here, right? So in that situation, so this is point B here. In that situation, the net force in that direction, all right, it's equal to just normal force, right? And then the net force in that direction, the centripetal direction should be just equal to mv squared over r, right? You can ignore this direction, okay? What this force is doing at this moment is just slows down the velocity, okay? Now, if this velocity is not being slowed down, then there might be a friction force or the driving force. Let's call it driving force, okay? So there might be driving force here, okay? FD, driving force over there, okay? Which could be the same length, at the same magnitude, okay? If the speed is consistent, constant. So from these two, you can come up that normal force should be just equal to mv squared over r, right? You should set the two equal to each other, okay? So this is at that point, B point, right? Right, it's so mg, so we don't have to care about mg's because mg's, yeah, it's perpendicular to that direction, yeah. So then they are independent of each other, okay? So you can take a x direction and then you can take a y direction, right? So then pretty much we can just focus on the x direction this time, okay? Because that's all you needed. You are looking for a normal force, all right? So in the x direction, then net force is equal to normal force, and from Newton's second law, the centripetal force is equal to that. That's also in the same direction, okay? So then normal force can be calculated here, Yeah, you can set up the y direction, net force, whatever, but it's not relevant to looking for solving for n. Okay. All right. Now, at point C here, at the top of the track here, all right, you can see again, there's this guy. So again, we'll just focus on the direction that is in the centripetal direction or pointing towards the center of the circle. So the mg here, and then at the top here, now the track should exert a normal force, okay, downward in this direction, because the normal force is always in the direction that is in the normal direction of the surface of contact. Okay, so in this case, the surface of contact is this here, inner part. Okay, so the normal force will be pointing downward. All right. So when it's at this point C at the top here, net force in the centripetal direction should be equal to, you should add the two up, right? M plus mg. Okay. And then from Newton's second law, it should be equal to the mv squared for the centripetal oscillation. Okay. So then again, on these two, you can set up that they equal to each other. Okay. So then m will be equal to mv squared over r minus mg. Okay. So the mg is always pointing downward. Okay, but normal force is always perpendicular to the surface of contact. Okay. Question you might have? Okay. Now, if not, in part D, it tells us that the radius is equal to 10 meters. So it's asking what would be this V, or minimum V, at point C, so that the motorcycle doesn't fall off the track. Okay. So in order for the motorcycle to stay on the track, right, then you should have this normal force presented, right? If your normal force is certain number, say maybe 10 newtons or 20 newtons, if it's positive, right, then there's interaction between the motorcycle and the track. So that means they are still in contact, right? Now this normal force can decrease when it reaches 0. Okay, so that means their contact is very, very weak, right? And then if it's negative, that means it falls off, right? Or actually, it will not be negative, because when it reaches to 0, then it starts to fall off. So there's no contact, then there will be no normal force. Okay, so then that's so if the motorcycle falls off the track, that means your n equal to 0, right? Normal force equal to 0. So then you can set up that n equals to 0, right? So then it falls off, right? So in the previous part here, you see the n is equal to mv squared over r minus mg, right? So that means when mv squared over r minus mg equals to 0, then it falls off the track, okay? So then from here, you can see the m and m will cancel out because it's 0 on this side. You can divide everything by m. It's still 0 on the right-hand side, but this m will go away, right? So your relationship then becomes v squared over r equals to g. Okay, so you are given r, g is the 9.8, so then v can be calculated. Okay, so then in that case, v squared is equal to g times r. You can multiply both sides by r, get rid of r on the left-hand side here. So then v squared equals to g over g times r. So v equals to square root of g times r. Okay. then square root of 9.8 meters per second square times 10 meter. So then V is equal to 9.9 meters per second, or roughly 10 meters per second. Okay, very close to 10. All right. Questions you guys might have? Okay, so if that's clear, we can move on to the next. Put this guy back. All right, so the next section talk about fictitious forces. Okay, so that means sometimes you feel some force. For example, if you are turning, okay, say if you are turning to the right, then you feel like you are being thrown out towards the left, right? So if you feel like there's a force pushing on you towards the left, right? But if you take a second look over here, so there isn't anything pushing on you, right? There's no object exerting force on you. Just because you are moving on the car over here, your body actually has a tendency to remain its original motion. So it's originally going in the linear direction there, right? But the car actually turns, right? So then you feel like you have the tendency to keep that constant velocity over there, but the car turns, right? So in the frame of the car, so you guys are kind of separated, okay? So actually, no, there's nothing pushing on you, but you feel like you are being thrown towards the left. That's because the car is turning, okay? And that's because your inertia, that's like for Newton's first law, okay? So in this case, you are actually having the taking the car as your frame of reference. Okay, so in that case, the car is turning. If the car is turning, even though its speed may be still the same, but the direction changes. So that means the car has the change in direction of the velocity. Okay, so when the car's velocity has changed, that means the car has acceleration. Okay, so then your frame of reference of the car, it's not an initial frame of reference. It's called a non-initial frame of reference. Okay. So if you have an object as your frame of reference, it has oscillation, then it's a non-initial frame of reference. If you take that as your frame of reference, then you might experience the fictitious force, okay, which is the your perception of a force on you, but actually it's not a real force. It's a fictitious force, okay. In general, we take the Earth as the initial frame of reference because the Earth is very large, and then we treat it as it doesn't have a oscillation. Okay, but in reality, if you think that the Earth actually rotates, okay, and then it's also like rotating around the sun, so it actually has oscillation. Okay, so it self rotates. That means it has circular motion. Okay, and then it's rotating around the sun. That's a second rotational motion. Okay, so the um, so technically speaking, the Earth is not a frame of reference, but because it's so huge, so big compared to the object we are studying, so usually we treat it as an initial frame of reference, okay? Because we are inside the Earth or we are on the surface of the Earth, then we also share the same rotation of itself, and then rotation around the sun. Okay. All right. Now, if you have been riding on the merry-go-round here, you also experience the fictitious force. That is, you feel like you've been throwing outward. Okay, and then that's also called the centrifugal force. Okay, and that's because you are taking the merry-go-round as your frame of reference. It's a rotating frame of reference. That means it has oscillation, so it's a non-initial frame of reference. Okay. And then for you guys biology related major, you use centrifugals a lot. So that's the same here, because this is not, it's having rotational motion there. So it's a non-initial frame of reference. Okay. So then the object being like throwing towards the bottom until it hits the bottom of the test tube. So then the test tube will exert normal force, or that will be its centripetal force for the rotational motion. Okay. From a large scale point of view, like for the hurricanes, on the northern hemisphere, it always has this rotational, um, the clockwise rotational. That's due to the rotation of the Earth. Okay, so then there's a fictitious force on the whole system called the Coriolis force. Okay, so that's how the rotation of the hurricane developed, because the Earth's rotation. Okay. All right. So that's that section. So if you have non-initial frame of reference, then there's a fictitious force. Okay. The next section here in this chapter talks about another Newton's law. Okay. So we have talked about the Newton's first law, second law, third law. Okay. Now this is another law here. It's called universal gravitational law, or universal law of gravitation. So it basically says any two objects in the universe have attraction between them in the universe. Okay, so then like for the moon and the earth, they have attraction forces. For like any one of you, between you and me, there's this gravitational force. Okay. All right. And he proposed that the force is equal to a constant number times the mass of the two objects. Okay, so m, capital M, small m, if you have a larger mass, a small mass. Okay, and then divide by the separation of the two to the square. Okay, so f m1, m2, or capital M, small m, and then if they are separated by r, so then that's how you can calculate the gravitational force between any two objects in the universe. Okay. This G is called the gravitational constant. It's a very, very small number, okay? 6.67 times 10 to the minus 11, okay? That's in newtons times meters over kilogram square, all right? And then that's constant between any two objects, okay? No matter it's like small objects or larger objects like the sun, stars, even galaxies, okay? All right. So let's take a quick look on this example, right? So this one asks you to estimate the gravitational force between two sumo wrestlers, masses of 220 kilogram and 240 kilogram, when they are embraced and their centers are 1.2 meters apart. Okay, so capital M is 240, small m is 220, and then the separation, the r is 1.2. Okay, so they are kind of close to each other. What would be the gravitational force between them? Okay, you guys can give it a try. For the G, it's 6.67 times 10 to the minus 11. Okay, so see how big is this force, okay, when they are 1.2 meters apart. So gravitational force between them is equal to G times capital M times small m divided by R squared. So capital M is 240, small m is 220, R is equal to 1.2 meters. Okay, so basically plug in the numbers and then see how big is it. All right, so I think you should be able to finish that now. But we can take a quick look here. Okay, so this is 6.674 times 10 to the negative 11. All right, so if you keep everything in SI units, then you can ignore the units for right now. So then the result should be automatically in the SI unit, okay, of that quantity that you are looking for. Okay, so this will tell you. Now there's a square here. Don't forget that square on the R, okay? And then I think everything else should be straightforward, okay? So 2.45 times 10 to the minus 6, okay? That's the force. And then the force should have a SI unit of newtons, okay? So you can put newtons down here directly at the end. If you plug in everything in SI unit, okay? All right. So you can see it's a pretty small number, right? It's 10 to the negative 6. So that's why even though there's gravitational force between any of you guys in seat, you don't feel it, okay? Because it's going to be a very small number. All right. So the same happens to the when we are on the surface of the Earth, okay? So then the force between the Earth and any object on the surface of the Earth, okay? So then, for example, if there's a building on the surface here, then there should be gravitational force on the building. That's equal to, so gravitational force, we know it's equal to mg, all right? That should be equal to, use the same equation here, g, the gravitational constant times the mass of the Earth, the bigger one, times the mass of the building. And then divide by the r squared, the separation between the center of the two, okay? So the center of the two should be just the radius of the Earth, okay? And from here you can see, so the small m will cancel out, all right? That leaves us with just the gravitational acceleration, right? So then gravitational acceleration is equal to capital G times the mass of the Earth divided by the radius of the Earth, okay? So let me see if there's a, okay. All right. So the next one here, next example here, ask us to calculate the gravitational acceleration by using the mass of the Earth is 5.98 times 10 to the 24. Okay, so that's 10 to the 24. And then the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, so that's roughly 6,380 kilometers or 4,000 miles. Okay, but we'll take that number to calculate the G. Okay, so again, I can give you guys a minute to quickly calculate this G and then compare to what the G we normally have. Okay, so your answer should be close to 9.8. All right. So you should be getting 9.80 meters per second square, okay? If you put everything in your calculator correctly. So 6.674 for your gravitational constant, or times 10 to the minus 11 as your gravitational constant. And then 5.68 times 10 to the 24, that's kilo in kilograms as your mass of the Earth. Okay, and then this is the radius of the Earth. Okay, so 6.38 times 10 to the 6. And then don't forget to square it. Okay, now you can also use this expression to calculate the gravitational oscillation on any other planets that you know. Okay, so G is the same thing. Then the mass will be the mass of that planet, and then R will be the radius of that planet. Okay, so you can use this to calculate the gravitational oscillation on the moon as well. Plug in the mass of the moon. You can look it up online and then radius of it. Okay. All right. So next, the textbook discussed briefly about the tides of on the Earth, of the ocean on the Earth. That's due to the gravitational attraction of the moon, okay, and then also of the sun. So when the moon is over here, okay, so then you get high tides and low tides, okay, so over there, and then because of the gravitational attraction of the moon to the water, okay, and then yeah, I think for the sun, it's I didn't put it here, but that's due to the moon, okay. All right. So the last section in this textbook talks about the satellites and Kepler's laws. Okay, so the moon is the natural satellite of the Earth. Okay, and then we also have a lot of the man-made satellites, artificial satellites. Okay, in space close to us. Okay, but for Kepler's laws, there are three laws. Okay, I don't think we are going to look into a lot of details of the Kepler's laws, but they are based on a lot of data, okay, a lot of observations of the stars and then the other planets in the sky. So and then they kind of compile all this observation and then propose these three laws, and then later on verify by looking at the close by planets and to verify that. So basically, the planets orbiting the sun. Okay, so this is the first law, Kepler's law. Its orbit should be eclipse. Okay, with the sun at one of the two focus foci. Okay, so you place the sun on the focus here, on the left focus here. It could be on T as well. Okay, and then you can have an eclipse around it. Okay, so that's the orbit. Okay, and then a lot of times because the focus, they are close to each other, so then the orbit looks like a perfect circle. Okay, so for the like the Earth's orbit is pretty much a very circle, but it's yeah, slightly not so perfect, but it's we can treat it as it's just a circle. Okay, for most of the planets here. Okay, that we see in the solar system. All right, and then you can draw a eclipse by using like a straight line here. Okay, so a fixed line of rope, you can tie the two ends together and then fix the two focus points, okay, with the line there, and then you can draw it through, okay, like that. All right, so let's take a look on this example here. So in this problem, we are going to treat the Earth's orbit as a circular orbit, okay? So it says calculate the mass of the sun based on data for Earth's orbit and compare the value obtained with the sun's actual mass. Assuming the orbit is a circle and its speed does not change. Okay, so if the orbit is a circle, then you are having circular motion. Okay, uniform circular motion. The speed doesn't change, then it's uniform circular motion, right? So then you are going to look for the mass of the sun. Then the Earth is having a circular motion over here. So you can try to see, try to relate the gravitational force of the sun on the Earth as the centripetal force of the Earth, because the Earth is having a circular motion, right? So there has to be a centripetal force for less circular motion, and then that should be coming from the gravitational force from the sun on the Earth, okay? So try to combine Newton's law of gravitational, universal gravitation, and then the circular motion here, okay? To see if you can estimate the mass of the sun. So it tells you the actual mass of the sun is 1.989 times 10 to the 30 kilogram. Okay, but you don't use this number for your calculation. Okay, so you based on the gravitational law and then the circular motion, you calculate for mass yourself. Okay, and then compare to what you got to this number provided. Okay. Yes. All right, so to make the diagram bigger, I need to stop the sharing. It's like, is that better? Okay. All right. So let's take a look here. So if you look at the Earth here, the only force that you want to consider is the gravitational force, right? So then the net force on the Earth should be this gravitational force, and then that's pointing towards the center of its orbit, which is the sun. So net force is equal to the gravitational force. Okay. Now the capital M is the mass of the sun, the small m is the mass of the Earth, and then r is the radius of the Earth's orbit. Also from the Newton's second law, it should be equal to the mass times its acceleration because it's having circular motion, so then it's mass times the centripetal acceleration, v squared over r, okay? So these two should equal to each other. So then you can set up capital G, capital M, small m divided by r squared equals to small m times v squared divided by r, okay? So then the small m can cancel out, right? And then the radius r here will cancel out the square here because there's r square here. So you still have r remaining, but the square goes away. Okay. So you can see for the mass of the sum then should be equal to, now there's this r here, you can move to the other side of the equation. So in the numerator, denominator becomes numerator over there. Okay. And then this can move to the other side as well. So you will have capital M equal to V squared times R divided by G. Okay. So it tells you that G, all the G here is a constant here. And then it tells you the R is 1 astronomical units, which is given as 1.498 times 10 to the 11 or 496. Now, the only thing we really need is this V, the speed of the sun's rotational around the speed of the Earth rotating around the sun. Okay. And it also tells us the period of the Earth's orbit is 365.3 days. Okay. So that's that fractional days. That's why every 4 years we have a leap day, leap year, 1 extra day in February. And then it's so then in that sense, if this is t, right, the period, that means the time it takes to go 1 full revolution, right? So then you can calculate. So for the distance travel, then it will be the circumference here of the circle divided by that time t, right? So v then can be calculated by doing 2 pi times r divided by the period. Okay, distance travel should be the circumference, and then the time it takes is the period. Okay, so you can calculate that. So 2 pi times 1.496 times 10 to the 11. Okay, so that's in meters divided by the period of 365.3. So this is in days, right? So you want to convert days into seconds because seconds is the SI unit for time. So then multiply by 24 because there's 24 hours in a day. Multiply by 3600. Okay, that's 3600 seconds in an hour. Okay, so then this should be in seconds in the bottom here now. Okay, so that tells you your v, the speed of the Earth, it's 2.974 times 10 to the 4th meters per second. Okay, so it's roughly like 30,000 meters a second. Okay, so that's crazy fast. Okay, now you have that number, you can plug in over here. So 2.974 times 10 to the 4 meters per second square times this r, 1.496 times 10 to the 11 meters divided by 6.674 times 10 to the minus 11. That's in meters or newtons times meters over kg square. Okay. So you plug in all these big numbers in your calculator. It's going to tell you this is 1.989 times 10 to the 30 kilogram. Okay, which is exactly the same number given in the problem. Okay. So I think that's how the mass of the sun is being estimated. Okay, because you cannot directly measure the mass of the sun. Now you can also use the same technique. You can estimate what's the mass of the Earth. Okay, so given that we know the moon orbit the Earth about I think 29 days something. Yeah, roughly 29 days. Okay, but you can look up for the exact period. Okay, and then the distance from the moon to the sun. Okay, you can look it up. You can use those two numbers. You can also estimate the mass of the Earth. Okay, in a similar way. All right. Mm-hmm. Right. Yes. Yes. Mm-hmm. So that's the conversion from days to the second. Okay. All right. So then, so for the last a few minutes here today, um, we will have a quick look on the Kepler's second law and third law. Okay. So the first law says the orbital of the planet is a um, eclipse or the no, ellipsis. No, it's let me see. It's an ellipse with the sun at the one focus. Okay, so this also applies to the satellite that is orbiting a planet. Okay, so if you have a planet, so for example, for the Earth, then the moon is orbiting in a ellipse um, orbit. Okay, but it's very close. Again, it's very close to a circle. Okay, perfect circle. For other planets like Saturns or Jupiter's, they have more satellites. So then it's same here. So the satellite, the orbit of the satellite will be about its planet will be an ellipse. Okay, with the planet at the one of the focus. Okay. Um, the second law says, of the Kepler's second law, it says each planet moves so that the imaginary line drawn from the sun to the planet sweeps out equal areas in equal times. Okay, so over here, if the time is the same, so then the imaginary line drawn from the planet to the sun, this will sweep the same area. Okay, if say within 1 day or say 1 hour, they'll be the same. So this is again the 1 day here or 1 hour here, and it will be the same as the area here. Okay, so this is the same areas. All right. So with that, you can see that if the planet is close to the sun, then the speed should be larger, right? Because the arc length is longer here than over here when it's away from the sun. Okay, so when the planet is far away from the sun, then the speed of rotation is slower than it's closer to the sun. Okay, again, the same will apply to the satellites orbiting the planet. Okay, in a similar fashion. So that's the second law. The third law, Kepler's third law, says the ratio of the squares of the periods of any two planets about the sun is equal to the ratio of the cubes of their average distance from the sun. Okay, so yeah, the t squares over each other is equal to r to the q over each other, where t is the period and r is the average radius. Okay, so that's the third law. Okay, all right. I think um that will be it for this chapter. Okay, so we'll stop here for today. Um, for next week, we'll be checking on chapter 7, but chapter 7 will not be in exam 2. Okay, all right. So I will see you guys next week.